like to pleased to be able to introduce Mostafa Ammar, who's going to be talking to us on the evolution of networking and its research, a personal perspective. This clearly is a topic that has affected every one of us in this room and will continue to affect every one of us in this room because networking has literally changed the world, absolutely. But Mostafa is the Regents Professor with the School of Computer Science at the Georgia Institute of Technology. He's been with Georgia Tech since 1985, PhD out of the University of Waterloo, Ontario, Canada, and has worked with Bell Northern Research in Canada, first as a member of the technical staff and then as a member of the data networking planning. His research interests are in network architectures, protocols and services. And he's received funding from the federal and defence agencies, NSF and DARPA, as well as national and local industries, major firms including Cisco, IBM, Intel, Bell South and Sprint. Dr. Ammar has also served the networking research community in multiple roles, most notably as Editor-in-Chief for IEEE/ACM, Transactions on Networking, and other prestigious bodies. These awards include the IBM Faculty Partnership Award. He's received Best Paper Awards, Outstanding Doctoral Thesis Advisor, in fact has advised many PhD students. So I'm really pleased to be able to introduce Ammar today, Mostafa today, and I'm looking forward to hearing about the evolution of networking because it has been such a dramatic, world-changing area that has affected us all. So, thank you.
Thank you, Dean O'Brien. So, and let me thank you also. Is this too loud? I guess someone can, but I hope this means I don't have to scream. But so thank you for inviting me. This is, I think, already my second time. I think the last time was maybe 4 or 5 years ago. I gave a talk, probably exactly the same room. I'm happy to say that I have something else to talk about now, after 5 years. So that's always good. By the way, this is from the lyrics of a Jimmy Buffett song called Holiday. You can find it, I guess, on YouTube or whatever, but it's one of my favorite lyrics puts the internet, obsession that a lot of us have in perspective. Let's see. So, what I want to talk to you about today is a personal perspective on how I saw networks change, and particularly how networking research has changed over the years. So this is not a technical talk by any means. There's maybe some technical arguments in there, but I'm giving another talk at WCNC in a couple of days that's actually more about my research. But I had a lot of fun putting this together. In fact, I gave an earlier version of this internally at Georgia Tech, and had a lot of fun putting it together and giving it. And so this has been changed based on my experience in giving it the first time. But we're going to start with this concept of a time-traveling networking researcher. So this is a networking researcher that, and we're going to call him Marty, just for. But he actually gets in his in DeLorean and in 1985 and comes out in today, right, April 3rd, 2016. If you want to know how I did this, I'll tell you. But anyway, so he comes out today and walks out, and what he'll see, of course, is this. So by the way, 85 is about the time, it's actually the year I got my PhD, so that's why I picked that time. When he goes into the DeLorean, what the network looked like is this. This is essentially, it's the NSF backbone network, which is the father of the current internet. And it has, 5, 6, 7 nodes just scattered around the US. There were similar trials in different parts of the world, but that's about it. When he gets out of the car in 2016, this is what the internet looks like. This is probably the best way to visualize what the network looks like. This is scattered around the world. There are many, many dots. In fact, there are probably 70,000 dots. But each dot is actually a network made up of tens and hundreds of routers. Right? So we went from 7 nodes to 7 million nodes, okay, in 30 years. Again, when the internet started, in fact, this was not 85. This happened a little bit later. We were using it primarily for, there's a lot of email, but we considered an advanced application would be file transfer, which is I have a large file to move from one place to another. And pretty much every organization had what's called a FTP server. Today we have web servers. Those days we had an FTP server. And you put files and patches for operating systems and so on FTP servers. And this is really all we use the internet for, in terms other than email. Today, of course, the killer application is video. And I was happy to see that Netflix made it into Qatar without having to use a VPN, so that was great. But this is the technology that goes into something like Netflix is amazing. It's way beyond anything that anyone thought we could be doing. The people have been talking about video for a long time, but only recently, the last 5 to 10 years, are we able to get anything where we could replace TV and cable. Now, what changed also is the mode how we did networking research. So obviously the networks have changed, but in fact the people working on the research have changed. So in 1985, the people that were doing networks came from engineering backgrounds. And engineers basically were about designing and building things. We designed and built cars, we designed and built power generators, things that basically you did this. You designed it, you had some experience, obviously, some education, some background. You built it, and once you built it, you put it out there and you used it, right? The cars, everything like that, that's what we did. Cameras, everything was like that. And in fact, we had this vision that this is what we would do with networks, right? We would design them, use some theory, and build them, and then we would sit back and enjoy, the fruits of our labor. Again, as with any engineering, there has to be some foundation, some theoretical foundation. What I did is I chose a paper that this is by Bob Gallagher and Jamal Golestani from MIT. And Bob Gallagher is one of the fathers of information theory. He taught me a class in computer architecture a long time ago. But anyway, this is a typical paper from those days, right? Written by authorities in the field. The title was Flow Control and Routing Algorithms for Data Networks. Today this is the subject of several textbooks. If you want to write something, if you want to talk about these two topics, it's not something you talk about in one paper. Certainly, it's not something that is amenable to mathematical formulation with a solution that is optimal and we're done, right? This is a pretty complicated topic today. Then I think we had this maybe naive way of thinking about this, that we would do it this way. We would formulate it under an optimization problem, solve it, and we're done. And not only solve, this is like a huge thing. Routing and flow control is like two huge things. And in fact, flow control became flow control and congestion control today still continues to occupy people on exactly how to do it right. Now today, of course, here's what's happening. We realize that this is what we have to do. It's almost like feels like a nightmare. I think if someone had told me this in the 30s, I may not have gotten into this field. But basically, this is one of those things that never ends, right? It's not something that you could design and enjoy. You build it, maybe you measure it, you change it a little bit, and then you decide, okay, you're going to rebuild it, right? And then measure it again, and again, keep doing this. And this is, I think this is the accepted way we're going to live now in the era of the modern internet. The work looks, very complicated. It is, I've just picked a paper from SIGCOMM. one of the big networking conferences that has measurement in large data center networking and so on. Something else happened. In the conferences themselves changed, and the way we do work changed completely. I mean, I don't know if people realize this, but this is, for someone that has lived in this area for a long time, it takes a lot of flexibility and adaptation to survive in this world. So I went back to ACM SIGCOMM 85, which is, SIGCOMM is the main SIG special interest group that within the ACM for communication. In 85, it's a small conference, always wasn't really a well-known thing, had 22 papers. The number of authors per paper was just below 2. The minimum, there are lots of papers with single authors, but the maximum number of authors per paper was 3. Okay? This is, again, a simple title, Window Selection and Flow Controlled Networks. Try to even, talk about this other than in an elementary class on networking. People will laugh you out of the room. But then it was a topic of research. SIGCOMM 2016 hasn't happened yet, right? So has 40 papers, okay, a lot, but look at this, 6.3 authors per paper on average. The minimum, no single author papers anymore, doesn't exist. This idea that you can do work on your own is gone, okay? There are a few 2-author papers, but there was a paper with 18 authors, okay? The sample, this is the kind of work that we're doing now, practical, real-time, centralized control for CDN-based live video delivery. The word wireless, that's the only thing that's missing. I think if you had wireless, you'd have all the buzzwords that you need in one title, okay? But I mean, there's so much going on. The centralized control, real-time, video delivery, okay. Now, not to be outdone, I kind of followed this path. Sorry, I mean, I admit that's what I looked like in 85. But, this is what I was doing in 85. This is probably one of the last papers I wrote on my own, right, published in 87. And my work was very theoretical. This is from the appendix of this paper, in the Transactions of Communication. Today, of course, I track the community and my work. I still haven't managed to do the 18th thing. If anyone has 17 people needs an 18th, let me know. I'm happy to contribute. Maybe one sentence in the abstract, and that gives me. But anyway, I have 7 or 8. This is what this is like 6 people in this paper, which is maybe 5. And the work is very experimental. Probably not an equation to be found in this paper. A lot of measurement-based traces. A lot of work that that tracks the development in the community. But I think I want you to put yourselves in my place. You go to a PhD, you spend 6 years trained to do this kind of work, and now you have to live in a world like this. But I think this is, for any younger person, expect this to happen to you. Exactly where it's going, I don't know. But be flexible and adaptable, and we're always learning. It never ends, as you all know, of course. Okay, so this is this time-traveling network researcher. I'm going to get into kind of the main body of the talk, but let me just tell you a few caveats. First of all, this is very personal. So, there are a lot of people here with a lot of experience that may have been quite different. It's just what I've seen and what I experienced. I'm not going to talk a lot about my own work, right? So there will be a mention or two of things that I've done as it's relevant, but this is not a walk through all my contributions in research. The last thing I want to say is that if I sound critical at any point, I may. It is really not meant to be that. I mean, we all know that if you look back, you can find faults in things that have happened in the past. And I'm as much a participant in these things and probably as guilty as the next person in anything that went wrong. Right? So it's not meant to be a criticism. I just don't want to have to watch my words here in everything I say. But okay, so again, and also let me start you with the things that you should walk out with at the end. I'll repeat this list at the end. So the first thing is that we often ignore history in our either in the way we teach or the way we think about research, thinking that everything that happened in the past is wrong. I think, really, I think history is a very good source of new research ideas. Right? And I'll show you, an argument for that. The other thing to realize is that if you're living in the moment, and there is, in any community, but certainly in the networking community, there are things, there are people obviously that are loud, but there are topics that also are very loud, that you hear people talk about them all the time. And it's very hard to ignore it, and it's very easy to get sucked into all this hype of this loud thing. And sometimes, and I'll show you examples where people have spent a lot of time, and if you were in the moment, you would have thought this is going to take over the world and nothing happened. Okay, so if you like it, do it. If you don't like it, don't do it. But don't think too much about what the other world is, what the world is talking about as much. Obviously, you have to listen, but don't be influenced so much just by the how loud the arguments are. The other thing I should say, I mean, it will sound to, this is kind of the opposite of this. It will sound like I'm saying people wasted their time on doing certain things. There is no such thing, right? There is no such thing. When you do research, we're taking risks, and you want to encourage people taking risks, and every now and then, and maybe actually more often than not, you will take a risk and nothing will happen, right? So you should never think that if I do something and no one uses it, or it's not deployed or whatever, but if it's intellectually strong, there is always some value to what you've done. Right? So there is never such a thing as wasted research. Okay, so we're going to talk about networking, and any research really goes through both evolution and revolution. Okay, so evolution is the slowest one of these, basically saying that things change slowly, and you can see one from the other. You can see kind of the next step from the step before. But revolution, of course, was when things change completely around you, and you really have to kind of completely rethink everything. And both have happened in networking, right, to some degree. One of the things that have evolved over time is the scale, right? And I'll make arguments about the scale of networking. For the uninitiated, basically, all networking challenges are about scale, right? So in my class, networking class, I spent 2 lectures, about 3 hours, showing them how to build a network fully functional with the applications, you can, video or whatever, between 2 nodes that are directly connected to each other. You can probably design this, if you know enough about things, in a couple of hours and be done, right? So basically I tell them the first week is about this, how to do networking for small scale, and then the other 15 weeks are about how to manage the scale. Right? So it's all about scale. It's all about doing something, but not for a few people, but for a large number. So we'll talk. Scalability is going to be the one of the driving forces here, and I want to talk about change, right? So it's all about revolution and evolution are basically changes. So we're going to talk about 3 different kind of change modalities, if you will, that have happened in networking. The first one is the cycling of concepts, and I'll go through these in some detail. Basically, things go back and forth. And then there's things that go back or forth and never go back, right? So basically, there are things that change, but you never see, you never look back after that. And then there are things that you think are going to be changing, but you end up at a dead end. So we'll start with the first one. So in networking, as I'm sure in a lot of fields, you see things happening that remind you of stuff that happened before. And in fact, stuff that people have thrown away before shows up again. This is actually headlines from the New York Times. We all thought vinyl LPs are dead. They're not. In fact, factories now have a hard time meeting the demand. And there are stories about e-books actually dying as well because people are buying physical books. Now, so this has happened in networks all over and over again. So there are 3 things that I could talk about, but 2 things I could talk about, but I'm going to talk about the first one. Similar things happened in how we do networking. Networking in the early days was very centralized. Now it's distributed, and now we're back thinking about maybe centralization is not a bad thing. So, but I'm not going to spend too much time on that. I'm going to talk mostly about this many nets, one nets, many nets. So let me explain what I mean by it. So in 1987, this is one of the the famous textbooks by Misha Schwartz from Columbia University on networks. And if you went to that book, and I'll have a couple of occasions to quote from that book, but one of the things he sits and describes the different kinds of networks, right? So this is a listing, TimeNet, GTE, Telenet, Transpac, and so on. So these are different networks. Sometimes they're geographically based, like Transpac was in France, DataPac is in Canada. Some of them are functional. The TimeNet was for time sharing. ARPANET was a research network. Then you get these other kinds of networks, SNA and DNA. These are networks that were being sold as systems by computer vendors. IBM, you went to IBM and said, I want to build a network in my building. They say, oh, we sell you everything. The boxes, the protocols, the software, the hardware, everything. And we manage it for you. And it doesn't work with anything except our equipment and our software, and only our people know how to fix it, right? And that was fine with people. So there were different kinds of networks, one for work, one for home. America Online was a network that people used to subscribe to at home. If you wanted to experiment, you didn't touch any of these. You went to ARPANET and said, I need to play around with your protocols and so on. I just want you to think, if you lived in that world, you thought this was going to survive, right? And it was all about, can I sell more networks than my competition, okay? At some point, this is, we take this so for granted now. At some point, someone decided, no, we need one network for everything, for everywhere, right? And this, I would say, is a revolution. And, it's hard to track it down to one person, but, it's kind of an organic thing that happened. Right? But I just want you to think this was not an obvious thing that could to happen because of all the different constituencies and interests that people had, some of them making money, some of them intellectual and so on. So it's not an obvious choice, but it happened, right? And that you can think about what it is. We needed scale, right? We needed to, there was more and more demand for networking than IBM could sell networking products. So we needed, other people to do it, and we needed it to be cheap. So you couldn't afford the really expensive proprietary things that people were doing. So all of this kind of, I think, led us to this, basically, the way we think today of the network as one network. We have one network that connects the whole world and everything with all applications running on that one network. Now, the question I want to ask now is, are we seeing a reversion now to many networks? Okay, and but let's think about what this one network kind of did to us. So first of all, to have one network, you have to have agreement, right? I can't have you running IBM software and someone else running, someone else's software and someone running experimental. We had to all agree on the same system, right? But because the whole world has to agree, it has to be simple. I can't, say here are, 500 pages of contract, sign here because we all agree, right? The contract that we had to sign had to be simple. And as a result, the internet, in fact, the point of agreement on the internet is a very simple thing about basically the IP internet protocol being deployed everywhere on the internet. The other thing, of course, when you have this large scale, the one network, you can't have one manager of one network that is global. You have to have many distributed management, and so we had to have an architecture that it's all recognized today by people that work in this area of multiple domains, multiple administrations that kind of work together nicely. There's one other thing though, so that was nice. Those are the things that made it work. There was something else though, that when you had one network, it meant network research had to actually change. Right? So one of the things that had to change was you couldn't think of anything outside that network. If you came to me and said, I want to deploy, I have a better idea on how to do something in the network, but this network is everywhere and everyone is using it, no one would talk to you, because even though it's a better way to do it, it's not interesting because it has no practical value at this point. So it stifled innovation. Um, the, um, the other problem that we had was if you came up with an idea and you said, believe me, it works. Say, okay, so how would you really test it? Well, I can test it in my lab with 5 nodes. No, I need it to work in this 7 million node network that I showed you earlier. We say, well, we can't, sorry, because this network, people are using it for real stuff. You know, you can't disrupt them. So we had this issue of we couldn't actually test anything on a real network anymore. And so there was all this work on how to find experimentation environments. And actually, this has been one of those things that I think people have tried, but actually has not succeeded. There's so much money been spent on developing them. So these things, the M-bone, Q-bone, this bone stands from backbone, right? M-bone is the multicast backbone. Q-bone is the quality of service backbone. 6-bone is IP version 6 backbone. Planet Lab, Genie is the most modern of these. None of these approaches even the scale of anything like the internet. And so even if you validate on those, which is already a challenge, you're still not sure this thing's going to work. So we still have this problem, and this is really the result of having everything in one network. So what I think is happening today, but we're seeing the beginnings of it, so I could be totally wrong, right? But I'm going out on a limb here to say that what we're seeing is the beginnings of the many networks again, right? And I'll show you some examples of this. The main reason really is now we're not about connectivity anymore. The reason the internet or the network exists primarily is for content delivery. Right? That's where the money is. That's where the bulk of the traffic is, the volume. And that's not going to go anywhere. Content providers have their own interests, right? They want to maximize quality of experience because they want you to pay to subscribe. They don't want anything between them and you. So Netflix, if they could have their way, they don't want anything. They want to be in charge of the entire thing. Because if the quality of the video is compromised when it gets to you, and you're going to complain, and they want to be in control to fix it for you. Okay. The other thing I would argue at some point is that the scale now is actually we're seeing another kind of inflection point in the scale, where having one network is going to be also very difficult to manage. So one network has a kind of a sweet spot of where we are now. To manage even more scale, more people on the network, more devices on the network, we need some other model. So I'll give you an example. You may or may not realize this. If you use Google, you may not actually be using the internet. Okay? So this may come as a surprise to everyone. But here, this is, so now this is where it gets a bit geeky. But this is something called traceroute that if you're in a networking area, you know what I mean. But basically, if you look at the path from your device to Google, certainly at Georgia Tech, I haven't tried it here, but I suspect something similar is happening here as well. You basically are going through your access network, which is Georgia Tech, and then you're going to the Google network, straight, right? So the access network and Google, there's nothing in between Georgia Tech and Google at all, okay? And Google wants it that way. It's actually by Google's design. They couldn't actually come and take over Georgia Tech's network, but the next best thing is to connect directly to it, so there is nothing between Georgia Tech and them. Even worse, we all know, for example, that the internet uses TCP IP, right? Now, this is again a bit geeky, but Google has decided that TCP is not good for them. Right? They want something better. And so they use something called QUIC, and it completely replaces TCP. And if you use Chrome and you go into Google, you're not using TCP anymore. And this is a way to look at the protocols that you're using. You're using something called QUIC. Okay? Now, it's even more sinister than this, if you believe. There's something called Google Fiber, which is actually coming to Atlanta, my hometown. Basically, what you'll find is that Google now is in the business of providing access networks. So they're going to come and provide fiber all the way to my home, very high speed, very reasonable costs. So in fact, if I subscribe to Google Fiber and I use Google, I completely stopped using the internet. I'm using Google's access network. I'm using Google's content provider network. I'm using Google's transport protocol, and God knows what else I'm using in the middle, right? So all the stuff about the internet is gone, right? And that's by design. Yeah.
Question, when you say Google's network earlier on with the trace route, are you talking about even like fiber links or talking about routers, like the infrastructure part is also fully Google owned?
So you mean yeah. I mean, basically, if you look at this trace route, what you'll see is there are a few routers that are Georgia Tech, and then after that, once we exit Georgia Tech, we peer directly with Google. So we go straight into Google routers.
But they would have their own cabling and wiring?
It's through an internet exchange, so they're peered with us, right? So it's a peering thing. So Google offers open peering. So if you come to Google and say, I want to peer my network with you, they'll say, fine, without cost. Because they want this kind of thing. And they want, we can talk about this. It's a bit geeky now. But, yes.
But the difference between this and the earlier mini nets is that it's transparent to me. I don't know that I'm on the Google network. I'm on the browser and I think I'm...
Yeah, absolutely. So it's a little bit better, right? It's a little bit better. But now what will happen, of course, is that when you use Google, you're going to use this network. If you decide you're going to go somewhere else, you're going to use some other network. Right? So, and the commonality might be just the plug at some point. Okay, so let me show you actually something else that's happening that you may or may not realize. This is a company called Sigfox that actually has strong presence in Europe, and it's coming to the USA at some point. Strong presence, I mean full coverage of France, Germany, Spain, and so on. What they do is they provide networks straight from devices to servers that completely bypasses the internet. They do it using some cellular technology, their own set of protocols, no TCP, IP, nothing. And they are they're in the Internet of Things space, so they're trying to address these very large, in fact, their homepage has this graph that shows, 40 billion devices at some point that will, if they all come on the internet, they will collapse. We'll talk a little bit more about that kind of scale. But basically, this is a total bypass network that takes clients to servers, no internet, right? So in this case, it's not actually transparent because you have to intentionally use this network compared to the other network. Now, this is a guess on a few observations, so who knows how this will develop. But you're seeing more and more of this change of going from one network to serve everything to these many ways of doing things. And this is kind of one way to think about this. And this happens all the time, in networks. And like I said, it's happening in centralized and distributed management of networks. I don't know if there's a lot of work on what's called visible light communications today. The problem is visible light communications is what we used to do, 200 years ago with smoke signals and things like that. Anyway, so I'll go back. All right, but just to be clear, there's nothing critical about this. I think this is natural. This cycling is a natural thing, and it's nothing bad. But it also gives you some insight on how you should do research, which means that every now and then you should just go back and look at things that people have dismissed and think, are they helpful? And in fact, I would argue that this is a geeky thing again, the software-defined networking world of centralized control came back from someone thinking, well, maybe distributed control is not a good thing, and centralized control, which used to be a bad thing, now is a good thing, and opened up a whole new world of approaches. Okay, let me talk to you about the second kind of thing, which again is interesting. So there are some things I will argue that will happen, and those are very fundamental and will stick with us for a long time. And there are many things that have happened in networking. I'm going to focus specifically on this TCP IP wins over OSI. This is actually quite revealing for people that have not followed this in great detail. So remember, when we went into this one network world, we had to decide on one agreement. So before that, there were many protocols and many ways people connected networks. When we decided we were going to do it in one network, we had to decide on one way to do it. Okay? And at that time, there were two kind of competing technologies. One was the TCP IP protocol stack, and one was the OSI, which stands for Open System Interconnect Protocol stacks. This is again from Misha Schwartz's book in '87. So this is what he says about these two things. He says TCP is an older standard than ISO TP class 4. ISO is ISO is the International Standards Organization that actually was in charge of the Open System Interconnect. And they had a transport protocol that was called TP Class 4. They had many classes. It is expected that TCP and ISO TP4 will coexist for some time. Remember, this is written in 87 by an authority in the field. But that use of TCP will begin to decrease. It is of interest, nonetheless, to describe briefly some of the features of TCP here. So what he's saying is, you know, you're taking the class out of this textbook. You know, I'm going to teach you a little bit about TCP, but you can ignore it because it's not going to live for very long. But anything I say, and he spends a lot of time on ISO TP Class 4, you better learn this stuff really well because that's going to be your future. Okay? You know, if you're a student, it's very hard to argue with this. You know, who am I to say you're wrong? You know? Okay, so this is a view certainly from that work. Okay, so at that time, people really had these arguments about why OSI was the better way to do it. Okay, so one argument was, sorry, this is an in-joke, and if you know football and baseball, American football and baseball, look for George Carlin's, just search that, and you will see a video on how he compares the two. That's the closest thing I can think of between TCP/IP and ISO OSI. So basically, OSI was a very professionally done standard. That is, it's run by all these government organizations that are in charge of telecommunications in their respective countries. They sit together, they discuss standards, and then they vote formally, and they decide which way to go. And so it was very hard for a company to come in and say, you know, I have this piece of software that I've been developing for 10 years. Can you please make it the standard? Because the moment you make it the standard, my sales will go up. So it was less subject to abuse by people that are there just to make money. TCP/IP, on the other hand, was developing standards, but they were calling them requests for comments. Yeah? I mean, how seriously do you take it? I tell you, here's how it works, and it's labeled, please comment on this. Okay, I mean, so you're not taking it seriously, so I'm not going to take it seriously. It's approved by consensus. They sit in these meetings, say, you know, you guys, what do you guys think? It says everyone is okay, and some people hem and haw, some people are, you know, there were no laptops then, but they were reading newspapers and stuff. Anyway, so they say, okay, no one is complaining, so we'll agree, okay? And then they had this crazy idea that, you know, you should not really specify this thing to death. What you should do is implement it first, write code, make sure it works. And then you go, and the specification is written by reading the code. And of course, you skip a few things. So it's not formal. You couldn't read it and write the code. You wrote it first, and then you wrote the specification. So there was something wrong with this. So obviously, if you looked at this, you said, I want to go with OSI, because it's just a better way of doing this. It turns out this implement and specify was a better way to do it because it works. You know, that there is no argument with that. The specify then implement, maybe there was something wrong with that. So as a result of all of this, there was a lot of these things called the gossip mandate. So this is in '89, the US government came and said, no more TCP/IP, right? This is crazy, you know, these are all, you know, these hippies doing this thing. We want to have something that works. So we want you to make sure to build OSI protocols and buy. So this is the US government saying anyone using US government money is going to buy networking equipment has to buy OSI protocols. No more TCP/IP stuff, okay? And there were other people. There was a UK gossip. There were other countries that followed with this. And, you know, here, you know, this, just if you don't believe me, this is what it, there were lots of articles on this. This is, you know, I don't know, I can't read the year, but this is 1980-something, 89. And here is a statement. Effective August 1990, the OSI protocol specified in gossip became the sole mandatory interoperable protocol suite and must be included in all proposals for new automated information systems and major upgrades which require network services. This is the US government saying this. Again, you're reading this, you're saying forget about TCP/IP because I'm not, you know, no one is going to buy it anymore. The US government is saying don't buy it. IETF, the people that were doing TCP were also buying this. It's not just, you know, so here's their RFC 1169. Unfortunately, RFCs survive forever, so they can't hide. Yeah. So here's what they said. You know, internet community represented by the Internet Activities Board and so on are fully committed to integrating OSI into the internet. As it is recognized that OSI is an international standard networking protocol. we are taking sound technical steps to integrate OSI. It's a joke because this never happened, right? In a fashion and on a schedule that assures current levels of service to users. So again, you're sitting there, this is so loud, coming at you from everywhere. You're saying, okay, I better really change the way I'm doing things. And in fact, we did some work, so I was a victim of this. We did some work on, this is from Infocom, believe it or not, on how to interoperate between TCP and IP, and a lot of people did this, okay? So for a lot of people, they thought, okay, we're going to transition. So actually, I spent some time working with the Army on, they had a lot of deployment of TCP IP, and they were saying, we have this thing, we have orders, we have to obey them, so we have to do this. And anyway, so we did some work on this. All right. However, TCP IP ultimately wins. I mean, there's no mystery here of what happened. But this is not what would have been predicted, right? So you're sitting in the middle of this. It's all this loud arguments about something, and it never happens. This is an article about this. This is, so it happened. It's funny that Texas was the first one to. So Texas basically said, no, I don't care about what the government is saying. We're going to do TCP IP because it's not working. One of the funniest things, so I pulled this because of this article, but if you look on the side, there's actually an interesting article, this one. So this is amazing because it's the same time that people are saying we're going to adopt TCP IP is the same time that people say TCP IP is not actually, we can do better, right? So this is, APPN is an IBM product called Advanced Peer-to-Peer Networking. This was their follow-on to SNA. And it says APPN tops TCP/IP in performance face-up. Right? So just as we were adopting something, there was something better that came along. Of course, never saw the light of day because it was very proprietary. Okay, so this is these things that happen, and there's a loud kind of discussion around it, and it kind of leads you in the wrong direction if you kind of believe it. Now, networking is full of things that happen that are dead ends. That people worked on them and then nothing happened after that. Multicast is one of those. I'll talk some more about this. But multicast, believe it or not, is actually coming back in some other. I mean, this is my pendulum thing. So it's not completely dead. But there are things. So I'll talk about it some more. But there's things that are actually definitely dead, never coming back. I don't see anything that's going to bring them back to life. ATM is one of them, but DQDB is many people have no idea what I'm talking about, so I thought it would be interesting. So DQDB stands for Distributed Queue Dual Bus, right? This is an IEEE 802.6 standard. Ethernet is IEEE 802.4, right? So which is very much with us, right? So the same people that brought us Ethernet brought us DQDB. And it's actually intellectually, if you look at exactly how the protocol works, is fascinating. It's completely useless knowledge that I have, unfortunately, but it's a fascinating way to run an access network. Okay, I just pulled something. So again, you go to conferences. There were sessions devoted to this. This is Infocom 92, 2 sessions on DQDB. DQDB enhancements and analysis of DQDB. So you go to this conference, you're a PhD saying, I got to work on DQDB, right? That's what's going to get me the job. It died very quickly after that, never to be heard of again. Right? Now, multicast is one of those things, and I'll try to be real quick here. Basically, multicast is a way to send data. It's actually what I'm doing now. I'm talking to you, and you're hearing it. I'm talking only once, and many people are hearing me at the same time. So it's a very efficient way to manage scale. And it saves on network bandwidth. So if you're multicasting, if you're sending the same message 3 times, this is what it would look like on a network. If you use multicast, you send it once, and then you get copies of it in the middle. So but it requires this data copying. Lots of work on multicast. Khaled will recognize some of these names. But anyway, I did a lot on multicast services, and so there are ways to use it if it's available. If multicast is not deployed today in the network in any large scale, but if it had been, it would have saved a lot of resources in the network. the problem is, the early systems of content distribution had multicast. And I'll show you, this is actually quite interesting. People don't realize this. So I promised, I think if you read the abstract, that I would answer the question, is the internet first or content distribution first? Which came first? It turns out content distribution is a really old idea, and people have been struggling on how to do it because they realized it was important. So I'll show you a system that's called teletext. And the way it worked is this. You had information in these pages, and these pages were broadcast as part of a TV signal, in the old analog TV signal. It was embedded in it, and the pages were sent to your device, but they were sent automatically to your device, and you picked one, and then you say you picked number 5, and so your device waited until page number 5 showed up, and it brought it up to you. And people were doing great things on this. If you see, this is what the display technology looked like. This has nothing to do with the networking technology at the time. But you could do radio stations. You can see here telesoftware. The BBC was running software downloads on this system. There are weather things and so on. You could even, in a version of this, you could book flights. You could do travel guides and so on. Right? So all of this is back in the early 80s, way before there was internet. So certainly we had content distribution. And it was done over this very scalable medium, which is the TV broadcast signal. Over the years, though, people have tried to replicate this large-scale thing on the internet, and these have come some of the numbers. In '98, John Glenn, in his 70s, went up in the space shuttle. It was a big event. They were broadcasted live on CNN, and they had 500,000 hits per minute. There was a Madonna concert in 2000 that was on MSN. They claimed 9 million people logged in, but basically, if you read the fine print, you'll see that many people just could not do it. There was quotes from people that tried to get on and couldn't because the network just could not handle and their servers couldn't handle it. Fast forwarding a little bit, Soccer World Cup on ESPN had 1.8 million unique users. NFL game on Yahoo just recently, in October of last year, had 15.2 million unique users. These are all live video streams. So we're able now to handle very large scale on the internet, but it took some time. Remember that we were able to do this scale on the TV way before this. And this is a network that does not use multicast. So there are all sorts of tricks that people are playing to do this without multicast. Now, multicast was let me skip some of these things, but basically one of the nice things about multicast was it allowed people to do content copying in the middle so that you can scale the distribution, but it never really saw the light of day. And one of the reasons is that other technology did not require changes inside the network. This is, again, this one network business. That because we had one network and we had agreement and everyone agreed on how it worked, you couldn't change, especially in places, because other places had to change as well, and there were too many of them, so we couldn't reflect the change ubiquitously everywhere. But the other thing that happened, and this is very fundamental in networking research, by the time people started thinking about multicast, they decided that they are not going to accept any solution that was not scalable. So they decided that if you could solve the scale problem in a small way, they will not accept it. And because of that, it became a problem of not having the services to justify the deployment. And of course, since you don't have the services, you don't have the deployment, you couldn't justify the services. So this is what I would call something, what I call the services connectivity model. And this has been fundamental in everything that has succeeded in the network today. That is, you thought about something you wanted to do, and then you built up the connectivity to help with it, and that gave you a way to do it better, and that improved the connectivity and so on. Anytime someone tried to deploy something in the network like multicast, right away without actually evolving it into bigger and bigger services, it completely collapsed. Let's talk a little bit about the future. This Yogi Berra is one of my favorite people to quote, so I take that with a grain of salt because prediction about is hard, especially prediction about the future. But let me argue that scalability is the one thing that we have seen over the 30 years. It's the one thing that has stayed with us forever and ever and ever. It's not going away. Here are some, so let me define it. I've talked about it. It's basically the ability to handle a large number of connected entities, okay? The question about what is the number, what do we consider large, and that has been changing over the years. So we are never good at this. We always predict that we're going to hit some scale, and we're always wrong, and typically on the downside. So here's a quote from an RFC. David Clark is, again, one of these authorities in networking at MIT, and he's been around, for forever, has a lot of contributions. This is from something he wrote in 1982. The guidelines currently recommended are an upper limit of about 1,000 networks, okay? If we imagine an average number of 25 hosts per net, this would suggest a maximum number of 25,000 hosts, okay? It is quite unclear whether this host estimate is high or low. I mean, he didn't even think he thought maybe he was too high. Things were going to be smaller than this. It turns out, he says, but even if it's off by several factors of 2, it turns out I did some number calculations, it's off by a factor of 2 to the 14 or something like that. So even David Clark, who I admire a lot actually as a visionary, could not see this coming, what we have today, okay? So this is how this is where the numbers are today, okay? We have 3 billion internet users, which means there are still 4 billion out there that are not using the internet. The number of connected devices is 10 billion, predicted to grow to 40 billion in 4 years. Okay? There are lots of issues. There's IP, of course, as many know. The main protocol is IP version 4, and that has 32 bits for an address. That is gone. I mean, actually, we're completely out of IP version 4 addresses. With a lot of tricks to prolong its lifetime, we have to, IP version 6 is taking over slowly. One thing that surprises me, there is something called the autonomous system number, which again, I never thought would ever be exhausted, that had 16 bits. There is now use of 32-bit autonomous systems because these are the networks of networks that we use. So one conclusion that you could reach, and this is again me going out on a limb, is that one of the things that is breaking down is our perception of what will work, of one network, covering everything, is going to break down once we hit these really large-scale numbers. Okay. So I'm predicting, okay, there's a video, I guess, you cannot, unfortunately, I can take it back. So that we will become more and more, we will live more and more in this many networks world, right? And going back to the question that today it's happening but maybe invisible, that this will become even more visible to us today. Okay? And one of the main reasons is this Internet of Things that, it's a buzzword, but actually it's real. I mean, to some degree, it's happening already. So it's not really about a prediction. That the level of demand is going to get very high. I mean, if you've never seen them, one of the very popular devices in the Internet of Things is the pizza button. I don't know if anyone knows what I'm talking about. So this is a button that communicates either through the Sigfox network or through your Wi-Fi network. You put it on the fridge. It's got wireless capability, and every time you press it, you order a pizza. And actually, Amazon has similar things. You can get a box of Tide. They sell you for this thing for $5. You put it in the fridge. When you run out of Tide, you hit the button. They send you Tide 2 days. It's at home. So think of now everyone has one pizza button, one Tide button, one milk button, one jam button, and so on. And all of these are communicating on the internet. 40 billion is going to sound too small at this point. And all of these are not going to be able to go on the internet. In fact, we need some other infrastructure. There's no reason why the packet that orders pizza needs to go on the internet. It's not really meant to do that. And I mentioned Sigfox earlier, but it's really designed specifically for that. They sell devices that operate directly on their network, so you don't actually have to go on the internet. And their main selling point is that they are offloading the internet, and they have counters on how much traffic they've offloaded from the internet as of today. This is one of my favorite. Anyway, so I like the Internet of Things, but it's maybe the Internet of way too many things. Okay, this is actually an editorial in the New York Times from a few months ago. It's actually very funny. You should read it about how this thing, how she bought a $99 thing to improve her $20 smoke alarm, but it didn't really do any good. Okay, so let me just leave you though with one challenge that I think I kind of referred to at some point, is that although we're talking about all of this, there is still a large portion of the world that actually has no internet connectivity whatsoever, and I think that remains to be a challenge. Remind you of the takeaways. Basically, history is always good. You know, it's important that we teach it at least. I think we don't do as much of that in our classrooms. Listen to what people are saying, but don't be swayed by how loud it is. You know, question it. You know, I've shown you where I've gone along. So I mean, I think it's natural to follow that, but don't always believe that this is going to be true. Again, no such thing as wasted research, because everything that has been done, even though it's not deployed, we've learned something from it. So thank you.
Outside scalability, what is one major breakthrough that if was solved, things would change radically, quantum leap in how we perceive networking?
Really, scalability, I mean, scalability is it, right? And I think what you see is we've solved scalability for delivery of, it's a moving target. It's not a first number, but it's moving in lots of different dimensions. One of them is the dimension of the size. You know, if you can look at how many people are in that set of people using that. The other, of course, dimension is the service. So scalability for the pizza button is very different for scalability for video, for Netflix. And the solutions are quite different. But I think a lot of them, I mean, Netflix actually has something similar going on like Google. Basically, Netflix is deploying services very close to the user so that they don't have to put up with you traveling through the wild network. And they don't have a mechanism yet to get all the way to you like Google Fiber, but they might reach agreements with people to do that. So it's still scalability, but maybe there are dimensions of this that have to be addressed. But, yeah.
Sorry, this is sort of a technical question, but can you explain exactly what made TCP/IP win over OSI? Because that part is kind of vague to me. It seems like OSI was a thing.
I'll tell you. There are a couple of things. So the first, and I know I skipped over it just in the interest of time, but basically, there are two main reasons. One of them is TCP/IP was essentially free. So it's hard to remember these days, but when you bought Microsoft Windows, you actually did not have networking installed in Windows 95. You just got it. If you wanted to communicate over the modem, you had to buy something to patch your operating system. However, TCP/IP got rolled into the BSD, Berkeley software distribution of Sun OS, of the Unix variants that was used everywhere. So a lot of people were using it just because it was available and it was free, right? So you got a lot of people using it, lots of experience, debugged. TCP got better in congestion control and so on over that time. The other thing is a lot of the OSI standards were vaporware. I mean, they were written down meticulously. If you read the documents, it was all sorts of jargon. Everything was fully specified, but no one had built them. And so when they went from specification to actual implementation, it's not that the protocols were bad. In fact, some of them were actually better. That when the first implementation is always bad, and you have to experience it, and so there was very little product. I mean, you said, so the government said buy it, and then you went and say, do you have it? They said, sorry, I don't have it. Come back in 3 years. Meanwhile, you have to run a network. One of the things that happened in the gossip mandate was funny, is that at the very end of this is the government document, there was a waiver process. So if you said, so they said you have to buy, you know, to OSI, unless, and then unless basically if you couldn't find it. So there was a big business in these waiver documents. You filled out this form about in triplicate, about exactly why you could not find it, you know, get letters from vendors and so on. And they said, okay, you can buy it. So people were buying, even during the gossip mandate years, were buying more TCP IP than gossip. And so at the end, you know, everyone gave in. There was and I didn't show you some of this discussion, but there was some, you know, the same people that issued gossip issued never mind, you know, kind of thing. That's, you know, it's not happening, so we're taking it out, taking it back, and let's go back to whatever the market gives you, use it. So that's how it went. Let me take some other questions and come back.
When does net neutrality fit into all of this?
So that's a good point. Net neutrality comes from the one network world, right? So it's the question of does Google and Netflix and you know Yahoo and all that have equal rights to your access network, right? To Comcast's access network. And you know, net neutrality basically says my access network is going to treat them all equally. Google is not allowed to come to my access network and say, you know, I'll pay you more if you give me priority over my traffic. So it's a product of this one network. You can argue that this many networks may not have that issue whatsoever. I mean, Sigfox doesn't need to worry about network neutrality because they own the whole thing, right? You know, Google Fiber, of course, will have to play nice that even though Google owns it, they're not going to give priority to YouTube over Netflix, say. Or if people find out that they are, then you know it could be.
Is this the reason that we're going back to many nets then? Is because
So if we do go to many nets, it will be you know, network neutrality is going to be moot, right? There is, I mean, in fact, we're beginning to think about the research agenda around this, about how to deploy this many nets, but it has to do with how you structure the access network. So there's possibilities that you can structure the access network so where you know net neutrality stops becoming an issue.
So when you speak of many nets, you're really speaking of many different sets of protocols and standards.
Right.
But the physical substrate itself is being shared by all of these.
Right.
So given that, how does the scaling up issue even factor, considering that eventually you're restricted by the physical substrate of not
Yeah, so the substrate, so of course, one way to do it, for example, would be to have the access network be just a physical network provider, and then you have logical things going on it. And the physical, you know, bit moving is going to have to be either proprietary or standardized, but that's not the issue. You know, anything above that becomes proprietary or becomes really the domain of the one that owns this network, the logical network. So I mean, as you saw, Google basically can totally ignore. They can't ignore, you know, the Wi-Fi and Ethernet and so on. But they have no interest in that. But they can certainly ignore TCP and HTTP even. QUIC is a replacement for both TCP and HTTP, and they have shown that it can happen. But they have to be in control of both ends. They're in control of your browser, they're in control of the service, and they can do everything. Right? So, so it'll have to be a change on how we do things.
So how do you see information-centric networking in the realm of all this?
So information-centric networking it's basically, you know, so I have sometimes kind of oversimplified views of things that sometimes are really wrong, but information-centric networking is all about addressing. It's just how you describe what you want, okay? And so it operates at a kind of an orthogonal level to all of this. So you can think of information-centric networking being, you know, being in, you know, working with everything or anything. So it's not necessarily a one network or, unlike net neutrality, which is specifically a one network phenomena. I don't think information-centric networking cares. It could be deployed. Now, whether it will be used or deployed is another story, but it doesn't really have any direct, you know, the one network, many network argument or the scalability argument may not have a direct bearing.
I guess I was trying to argue that you might look at the one network argument from that angle now, not from the access network end. That back to content delivery, right?
Oh, I see. That basically, yes, with information-centric, you're building an overlay that looks like a separate network. And in fact, I mean, this is I think the discussion that we were having just now about the substrate. So basically, one way to provide many networks over a shared thing is through some kind of virtualization. And so information-centric network gives you some virtualization that is at a higher level instead of a lower level. So it could be. All right, thank you very much.